Precise, mobile manipulation of small everyday objects. Many mobile manipulation tasks, such as grasping a knob to pull open a cabinet or pressing a light button, require precise interaction with small objects, where even a small deviation can cause failure. In this paper, we develop Servoing with Vision Models, a closed-loop framework for precise, mobile manipulation of small everyday objects. What makes these tasks hard is getting to an accurate pre-task pose around the small target object. Open-loop control does not work because inaccuracies in perception and control prevent correct engagement with the small interaction site. This necessitates a closed-loop approach. Our proposed approach, SVM, marries together visual servoing with large vision models. We use large vision models to specify targets for the visual servoing module. For objects that have a well-known semantic category, such as knobs, we use an open-world object detector. For objects which do not correspond to a semantic category, such as one of many buttons to turn off the lights, we leverage point trackers to continuously track a user-defined interaction site over the course of visual servoing. One problem, however, still remains. The use of visual servoing with an eye-in-hand camera for manipulation tasks suffers due to occlusion of the environment by the end effector, leading to erroneous detections. Even when the target object is not occluded, the presence of the end effector in frame, an out-of-distribution object, can lead to incorrect detections. We mitigate this issue by outpainting the robot end effector to obtain a clean view of the scene, and find that this improves the detection performance of the vision system. Here's an overview of our method. Starting from an input RGBD image, SVM first paints out the end effector using a video outpainting model, and then uses vision models to continuously detect the target object or track the desired target point to compute 3D servoing targets, which are then passed to a servoing module to obtain whole body control commands to convey the end effector to the target location. We test SVM across several real-world tasks, grasping a knob or handle to pull open a cabinet, and pushing onto buttons and books and shelves. Our focus is on generalization. Therefore, we exclusively test on previously unseen instances in novel environments not used during development in any way. More specifically, we conduct experiments on 6 tasks across 10 environments from 6 buildings. We obtain a 71% success rate on these tasks, 0 shot, on novel objects in 10 previously unseen environments across 6 buildings, outperforming ablations as well as baselines from prior work. Slight errors in getting to the target cause the end effector to slip off, leading to failure for the open-loop baseline, whereas our method is able to successfully complete the task. Note the quality of the detections in red is good. For the pushing task, we observe a similar failure for the baseline, whereas SVM successfully turns the lights off. Note that the quality of CodeTracker's tracks in blue is good. Erroneous detections without in-painting cause the end effector to hover around the starting location and for execution to fail, whereas with in-painting the target is correctly detected, leading to a successful execution. Next, we compare our method to robot utility models, an end-to-end imitation learning policy trained on large-scale data. RUM is trained on a dataset of 1,200 expert demonstrations for opening cabinets and over 500 demonstrations for opening drawers across 40 environments. We find that our method substantially outperforms RUM on a paired evaluation across 9 unseen environments from 6 different buildings. Note that RUM was not trained on knobs. We qualitatively compare to Foresight and find that it suffers due to occlusion. We also find that occlusion is a challenge in other robotic setups too, such as Droid, where DEDIC's most confident prediction of the handle is on the end effector. However, just as in SVM, outpainting the end effector helps detect the correct handle. Finally, we characterize the failure modes of SVM. We find that 35% were perception errors despite using a vision foundation model, and 65% were execution errors where insufficient precision was the dominant cause of failure, informing what future research should focus on. In summary, we demonstrate that servoing with large vision models, including detectors, trackers, and in-painting models, enables precise and generalizable mobile manipulation, significantly outperforming baselines such as open-loop execution and imitation learning trained on large datasets. Thank you.